Okay, here we go. This is 8.1, inverse trig functions. So we just watched the review on 6.2. We know about inverses now. In order to have an inverse, you need to be a one-to-one function. So that's what this section's about, is restricting these trig functions to become one-to-one. So let's get started. Okay. Down below, you see that the sine function, so over here, the sine function goes on infinitely, which means if I drew a horizontal line through it, I would intersect it an infinite amount of times, meaning it is not a one-to-one function. Well, just like you've seen before, it is very possible to restrict any function's domain to make it one-to-one, which is what we're going to do with the sine function. Now, the most common domain restriction for sine used everywhere, you can make up your own restrictions and make it one-to-one, but the most common domain restrictions for the sine function are going to be from negative pi over 2 to pi over 2. And if you see that little piece of the graph, if we restrict it to that, then here is what we get down below. This is the graph of the restricted sine function. So that's the graph of the restricted sine function. And since now it's restricted, of course, if I were to draw a line through it, I only intersect it once, which means, yes, sine is now a one-to-one function with a restricted domain. And the domain and range are there already for you, but I'll put it into interval notation just in case you needed a better view of that. So, okay, so for the domain restricted sine function, its domain is negative pi over 2 to pi over 2, and its range is still negative 1 to 1. Now guess what happens when we find the inverse? Your domain and range will flip. So as long as we have those written down somewhere, we know what we're working with. Okay, so with that being said, the restricted sine function with the given domain of negative pi over 2 to pi over 2 is now going to be a one-to-one function, which means now sine will have an inverse, okay? Sine will have an inverse. So let's go to the next page and see what that's all about. Finding the inverse sine function. Okay, so in these steps is where we're going to find the inverse sine function. So number 1 says, start with the restricted one-to-one sine function, list its range and domain. So that's everything I wrote on the first page. So we'll do it again. So come down here. And then that's good, that's good. So here we have y equals sine of x. Remember, this is one-to-one. Its domain from the other page is negative pi over 2 to pi over 2. Its range is negative 1 to 1. So that's all we wanted to do in this step. Now in the next step, it says, find the inverse of the sine function and list its domain and range. So we go through the process of finding the inverse, like we did on the last set of notes in 6.2. So step 1 is already done. It's already listed as y equals the sine of x. Step 2, we interchange. X equals the sine of y. So remember, we interchange. Step 3 is solve for y. Now the question is, how do I get y out of the sine function? How do I get y all by itself? Well, we don't divide by the word sine, because that would be a sin, right? That is not allowed. So if you were thinking of doing this and getting x over sin, that would be incorrect, because you have just divided by a word, not a function. And what we call that is you have just done a sin, right? You have sinned. Do not do that, okay? Bam, 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 bam. There we go. So again, how do we get this y out? Well, the only way to get y out of the sine function is to compose both sides with the inverse sine function. So I'll write that in here for you. So 3. Compose with the inverse, which means I'm going to have, how big is that? Okay, I'm going to have inverse sine of x on the left side equal to inverse sine of the sine of y. Now, if you remember that if they are true inverse of each other, then if I said f inverse of f of x, this means that the functions would undo each other and leave me with x. So this means that on the right side, the inverse sine function and the sine function will cancel each other out or undo each other and just leave me with y. So I would get the inverse sine of x equal to y. And there's your inverse. So step 4, state it as the inverse, and say f inverse of x equals the inverse sine of x. And now list its domain and range. Well, looking back at the top left, look up to the left. If that's the domain and range for the one-to-one function, then the domain and range for the inverse function, all you have to do is flip those. Just flip them. So now the domain of the inverse sine function is -1 to 1. And the range of the inverse sine function is -π/2 to π/2. Okay, great. So that's how we find the inverse sine function, and these are the properties of the inverse sine function. That's the domain and range of the inverse sine function. Down below, here is the graph of the restricted sine function and the inverse sine function. And remember, if they are inverses, they are symmetric about the line y equals x. And these look pretty symmetric. Here's the point, 1π/2. You flip it over the line, and you get π/2 and 1. Or the other way around. π/2 and 1, flip it across the y equals x line, and you get 1 in π/2. So everything's symmetric. Now, the most important part is this little graph down here. This graph shows us where the inverse sine lives. So this is what we want to reference when messing around with the inverse sine function, okay? Emails, let's see. Stuff. Okay. All right. So we said that the inverse sine function lives in between negative pi over 2 and pi over 2. So this graph is us looking at the unit circle. So put it in here. For the inverse sine function. Okay, so now we want to know where it lives. So we said it lives from negative pi over 2 to pi over 2. So the inverse sine function only lives in quadrants 1 and 4. It only lives in quadrants 1 and quadrants 4. Q1, Q4. Okay, now let's label the radians that are in these quadrants. So first, label the ones in the first quadrant. So there's 0 radians and pi over 6, pi over 4, pi over 3. Now, if we do a negative revolution, heading towards negative pi over 2, we live at negative pi over 6, negative pi over 4, negative pi over 3. And all of this is where, for all of these values in the first and fourth quadrant, is where the inverse sine lives. Inverse sine lives or exists, or whatever else word you want to make up with. This is where the inverse sine only lives. These are the only radian values that belong to the inverse sine function. Of course, you can use radian values in between all of these as well. Okay, but this is just showing you the regular unit circle of where the inverse sine lives. Okay, cool. All right. Something important to note, this whole paragraph is me yelling at you, the student. The inverse sine is not the same as 1 over sine of x. It is a notation, that negative 1. 1 over sine x is a reciprocal. A reciprocal is not the same thing as an inverse. Do not make that mistake, okay? Do not make that mistake. So up here, I can write it as inverse does not mean reciprocal. Okay, yeah, so this whole paragraph is me yelling at you. And depending on your calculator may have the button arc sine or inverse sine of x. All right. And usually to find your inverse button, all you have to do is hit second or shift and hit the sine button. And it'll print out the inverse sine of x. Okay. So now to evaluate an inverse sine function, we are going to follow the steps of the inverse. So everything you see here is how we will evaluate a sine function. So I'll break it down for you. If theta equals the inverse sine of x, then if we compose both sides with the inverse, with, well, the inverse of the inverse, which means that if I say sine of theta equals to sine of the inverse sine of x, this means we get sine theta equal to x. Because remember, sine and inverse sine are inverses of each other, so they would cancel, they would undo each other and leave us with x. So this is where all of this comes from, that box. Okay, and that's how we're going to handle the next set of problems. So when we're messing with inverses, you are calling on the unit circle backwards. So normally I say, what's the sine of pi over 2? You look at your unit circle and you say 1. Now I'm going to say, what's the inverse sine of 1? You're still going to look at your unit circle. You're going to look at where the inverse sign exists. And the inverse sign exists from negative pi over 2 to pi over 2. And the only place the inverse sign could be 1, positive 1, is at pi over 2. That's the only difference here. That's what we're doing with the inverse functions. We're calling on it backwards. So for the first one, we put in a radian value, and we get out a numerical value. For the inverse, we plug in a numerical value, and we get output of a radian value. So I guess for inverses, you can consider everything swapped, right? Everything switches, everything swaps. So that's what we're looking at. So let's try this example out over on the left. I mean, we kind of just solved it with what I wrote on there, but I want to show you the correct way. So we want to know the exact value of the inverse sine of 1. So the way we start these off is we say, let theta equal the inverse sine of 1. Then compose both sides. Now I'm going to skip some steps because I wrote it up here at the top right on your page. We're going to compose both sides with the inverse. So then, after we let theta equal the inverse sine of 1, then this means that sine of theta must be equal to 1. And now we have to think to ourselves, well, for what radian values on the interval negative pi over 2 to pi over 2 is the sine function equal to 1? And with that being said, you would reference this unit circle for the inverse sine function and spit out a radian value. And the only place sine can be 1 is at pi over 2 on these restrictions of negative pi over 2 to pi over 2. So come back down here. This means that the way we write our answer, well, on this interval negative pi over 2 to pi over 2, the only answer for theta is pi over 2. That's it. So I do recommend having your unit circle out for all of this. And it's pre-calc. You should have it. Like I said, tattoo it somewhere. Okay. B, we're going to work it the same way. Let theta equal the inverse sine of -1/2. Then compose both sides with the sine function. Then sine theta equals -1/2. But we need to look for the radian value on the inverse sine's restrictions. So go back to our unit circle for the inverse sine function. And if it's a -1/2, so if sine theta equals -1/2, the only quadrant you can be negative in is going to be quadrant 4. So out of these radian values, which one gives me -1/2? And that answer should be theta equals -pi/6. All right. Okay, so that's going to be our answer. -pi/6. Theta equals -pi/6. Just double checking my work. Yeah. Okay, good. Okay, excellent. And then for the next example here, you get to use your calculator. So I'm going to show you how to type these in your calculator. So let me stop sharing this screen. There's my face. And here up, I have the TI-30, the blue calculator, and the TI-84. So first thing you want to make sure is that your calculator is in radians. Same thing here, make sure we are in radians, and we are. So for the first example, it says, what is the inverse sine of 1/3? Okay, and I'm probably not sharing my screen, am I? I'm pretty bad at that. Yep, you're still staring at me. Okay, there we go. All right, so now you see the screens. Okay, so on the left is the TI-30, on the right is the TI-84. They're both in radians. So now I will say second inverse sine of 1/3. Enter. And we get 0.339. So I'll just round that up. Let me see. We said approximate, so I'm going to do little squigglies on the notes. 0.34. Okay. On the graphing calculator, same thing. Second sine button. I'll go find my fraction button. You don't have to, but it makes it easier. 1/3. Enter. Same thing. 0.34. And then next one is the inverse sine of 1/4. Let's say I didn't want to use my fraction button. That's fine. It's actually -1/4. Same thing. I get 0.25. So all this wanted was calculator work. So second inverse negative 1/4. There you go. And that's how you find your inverse buttons. There, you hit second, hit sine, second, hit cosine, second, hit tangent. Those are all your inverse buttons. Same thing over here on the TI-30. Second, inverse sine, second, inverse cosine, second, inverse tangent. Those where all your buttons are. They're right where your sine, cosine, and tangent buttons are. Okay, cool. Back to the notes. Back to you, Robert. Oh, thanks, Robert. There you go. And I wrote the decimal numbers there. Okay. Still working with the sine function. Okay. Where's my picture? There we go. Okay. Still working with the sine function. Remember that when you compose them, you take the domain of the inside function. So looking at the middle properties, when the inverse composes with f of x, meaning when the inverse sine composes with the sine of x, the inverse sine must take the domain of negative pi over 2 to pi over 2. So whatever value we get out of this composition must fall under these restrictions. Okay. Same thing going the other way. If f composes with the inverse, meaning if sine composes with inverse sine, then the sine function must take the domain of negative 1 to 1. So whatever happens here, let me do this better. So if we have a composition of this type, so this composition happens, we are going to get angles. And whatever angles we get must fit in these restrictions. Okay. Then, if we have a composition of this type, we are going to get a numerical answer. And whatever numerical answer we get, or output, must fit in these restrictions. Okay. So let's try it out. All right. So down here, looking at the properties above, oh yeah, we'll call this property 1, property 2. Okay. Which means this will help us figure out which composition are we working with on certain problems. So now letter A, inverse sine of pi over 8. Well, that looks like we're going to use property 1. That looks like the compositions in property 1, which means that when you compose these two, the inverse sine and the sine will cancel, giving you pi over 8. Now our job is to see if pi over 8 is in the restrictions negative pi over 2 to pi over 2. So this one uses property 1 from above. Well, is pi over 8 in these restrictions? Yes. But do you know exactly where pi over 8 is? Let's go back and reference our unit circle for the restricted sine function, for the inverse sine function. Well, pi over 8 is, guess what? In the first quadrant. Pi over 8 happens to be right there, which means pi over 8 is in negative pi over 2 to pi over 2. So this means that, yes, this radian value fits in there. Okay. Now let's go back down. So the way we state our answer is we say pi over 8 belongs to the interval negative pi over 2 to pi over 2. Now this funny looking symbol, the element symbol, means belongs to or element of. So since pi over 8's in there, this works. There's our answer. Okay. All right. So now, B, you have sine of the inverse sine of x. Well, this one looks like property 2 above. This looks like property 2. So you compose them, and the sine and the inverse sine will cancel, giving us 0.5. Now, what we want to know is 0.5 is 0.5. 0.5 is in the new restrictions of -1 to 1. And this is, of course, using property 2 above. Well, does 0.5 fit in -1 to 1? That is a yes. So our answer here is 0.5 belongs to the interval -1 to 1. That's easy. Okay. Moving down. Do it again. Inverse sine of sine of 5 pi over 8. Well, this is property 1. Property 1. Okay, which means that the inverse sine and the sine will cancel, giving me 5 pi over 8. Now, is 5 pi over 8 in the interval negative pi over 2 to pi over 2? Are we in that interval? Which means let's look back at our unit circle over here. And where do you think 5 pi over 8 is? So 5 pi over 8 is actually in quadrant 2. Again, the way to figure out where these angles are is 1, you can convert it from radians to degrees to figure out the quadrant, or 2, you can count radians, right? So if I were to do radian counting, again, there's pi over 8. Then I would add another pi over 8, give me to 2 pi over 8. Well, 2 pi over 8 reduces to pi over 4. And then I would count it again, and I would get 3 pi over 8. And then I would add another pi over 8, and I would give me 4 pi over 8, which happens to be pi over 2. Well, now if I add one more pi over 8, I get to 5 pi over 8, which is in quadrant 2, which means it is not in our restrictions. So 5 pi over 8 is not in But that doesn't mean we're done. This means we can fix it, okay? We can fix it, like Bob the Builder. Can we fix it? Yes, we can. And the only way to fix it is by using reference angles. We use reference angles, okay? Oops. There you go, pi over 4. Okay, so we fix it by using reference angles. So this means that I'll come back here and let me draw a little unit circle here. So here is (5 pi over 8), and here's pi. How many reference angles to get me to pi? Well, I'm going to need 3 more pi over 8s to get me there. So this reference angle is going to be 3 pi over 8. And now we wonder, is 3 pi over 8 in negative pi over 2 to pi over 2? Is 3 pi over 8 in negative pi over 2 over 2? Well, yes. (3 pi over 8 is here, which is in between pi over 2 and negative pi over 2. So this one fits in our restrictions, which means that we go with the reference angle, okay? We do the reference angle. Okay, so our answer here, our final answer is 3 pi over 8 belongs to negative pi over 2 over pi over 2. Okay, so if we get an angle that's not in the restrictions, we can fix it by reference angles. So fix by reference angles. Okay, next one down below. Sine of the inverse sine of 1.8. This is property 2. So this would just become (1.8). And what we want to know is 1.8 in negative 1 to 1. And the answer is no, and there's nothing we can do about it. We can fix radian outputs, we can fix angle outputs as long as it's using property 1. We cannot fix numerical outputs. There is no way to fix this numerical output. So what we say is 1.8 does not belong in the interval negative 1 to 1. Can't fix numerical. But remember, you can't fix numerical if it's property 2. Okay, great. There you go. That was everything for the inverse sine function. Now we move on to the inverse cosine function. And just like sine, cosine goes on infinitely. So if we were to draw the horizontal line through it, we would intersect it infinitely, which means it is not 1-to-1. But now we know it is possible to restrict any function's domain to make it 1-to-1. And the most common restrictions for cosine is going to start at 0 to pi. So it's from 0 to pi. This is how we make it 1-to-1. Okay, which is shown right below. Here is the restricted cosine function. So I'll write that down. Y equals the cosine of x. This is our restricted function, domain and range. Domain is now from 0 to pi, and range is still from -1 to 1. -1 to 1. Okay, cool. So there it is. We have now restricted it. And if I draw a line through it, I only intersect it once, which means it's a 1-to-1 function, which means cosine will now have an inverse. So let's go find that inverse. And very similar instructions, just like the sine function. Let's list everything we know about cosine. So y equals the cosine of x. The domain was 0 to pi. The range was -1 to 1. Okay, now let's find the inverse, just like we did on the last one. So step 1's done already. Y equals the cosine of x. 2 is interchange. X equals the cosine of y. 3, just like the last one, you are going to compose both sides with the inverse. So I'll get cosine inverse of x equal to cosine inverse of the cosine of y, which then leaves me with cosine inverse of x equal to y. There it is. We have the inverse. So 4 stated as the inverse. F inverse of x equals the inverse cosine of x. And now my domain and my range will flip. So look over here. That domain and range flips. So now my domain, -1 to 1. My range, 0 to pi. There it is. There's the inverse cosine and its restrictions, which is graphed below. So the pink line is the original cosine function, the restricted cosine function. The blue line is your inverse function. And once again, they are symmetric about the line y equals x, which means if I have this point -1 pi on the left, I can reflect it over the line to become pi -1. Same thing over here, 0, 1, reflected to become 1, 0. So graphically, they are symmetric. Algebraically, we prove they are symmetric. And that's it. Now, again, the most important part is, where does this function live? Where does the inverse cosine live? So again, this is the, I'll write that somewhere else. This is the unit circle for inverse cosine. Okay, so our domain says we are from 0 to pi. So the inverse cosine lives in quadrants 1 and quadrants 2. And now let's list all the values in these quadrants. maybe too far, but it's fine. Pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6. And again, all of this is where the inverse cosine lives. That's where the inverse cosine lives, quadrant 1 and quadrant 2. Okay, so this is the unit circle you want to reference when dealing with the inverse cosine. All right. Now again, this is me yelling at you. The inverse cosine is not the same as 1 over cosine. The inverse is not the reciprocal. So if I have to keep writing that above, I will. Inverse is not a reciprocal. Okay, and in your calculator, depending what you have, your button might say arc cosine, or your button might say inverse cosine. So just know they're both the same. And down here was the way to rearrange the inverse cosine by composing with cosine like I did on the sine function. So I'm not going to rewrite that. It's the same exact process that I did for sine. So with that being said, let's go ahead and try to answer the questions below. So for this one, find the exact value of the inverse cosine of 0. This means we say let theta equal the inverse cosine of 0. Then compose both sides with cosine, and you'll get cosine theta equals 0. But we have to figure out where is cosine equal to 0 on the restricted interval from 0 to pi. Which means we come up here, we look at our unit circle for the inverse cosine. And remember, we are looking for cosine, I should write that away. We are looking for cosine theta equal to 0. So what radian value in these quadrants gives me 0? And that is going to be pi over 2. Because cosine at pi over 2 is 0. Okay. There we go. Okay, so coming back here, this means that our answer is theta equals pi over 2. That's what we're looking for. Okay, moving on. Let's do it again. Let theta equal the inverse cosine of negative square root 2 over 2. Then cosine theta is equal to the negative square root 2 over 2. We have to figure that we want to know what radian value makes cosine the negative square root of 2 over 2 on the interval 0 to pi. Let you look at that for a second. So we, again, compose both sides with cosine. We get cosine theta equals negative square root of 2 over 2. And we have to wonder what value of theta gives me negative square root of 2 over 2 on this interval 0 to pi. So come back up. reference this chart, we are looking for cosine theta equal to negative square root 2 over 2. And if it's negative, this means it has to be in the second quadrant, because cosine is negative in the second quadrant. So we have to be somewhere in here. And the only radian value that can give me negative square root of 2 over 2 in the second quadrant is 3 pi over 4. That is correct. So theta would be 3 pi over 4. Which we'll put down here. Theta is 3 pi over 4. There we go. Excellent. So that's how we work those. And now we are going to do these inverse properties again like we did with sine. So remember, when you compose with a function, you take that function's domain. So if it's inverse cosine with cosine, inverse cosine obeys 0 to pi. If it's cosine with inverse cosine, cosine must obey negative 1 to 1. Okay, so we'll do this again. We'll make this one property 1. And this is for angles. Whatever angles we get, we must make sure they abide by that domain. The bottom one is going to be property 2. And this is for numerical. Whatever numbers we get have to fit in that domain. Okay, so let's try it out. A, inverse cosine of cosine of pi over 12. This looks like property 1. So this means we are just going to get pi over 12. Now, what we want to know is pi over 12 in 0 to pi? Well, come back over here. And pi over 12, it's positive. Where do you think it is? Quadrant 1, that is correct. Am I talking to myself? Yes. Here's where pi over 12 would be. Because if I did 2 pi over 12, guess where that would be? Pi over 6. So this is exactly where pi over 12 is. It's half of pi over 6. So come back here. And we have our answer. Pi over 12 belongs to the interval 0 to pi. There it is. Okay. And then next, cosine of the inverse cosine of negative 0.4. This looks like property 2, which means we'll get negative 0.4. Now we want to know, is this in the interval negative 1 to 1? And negative 0.4 is definitely in negative 1 to 1. Okay. And then C, the inverse cosine of the cosine of negative 2 pi over 3. Okay. Before we even cancel these out, let me see. Yeah, before we even cancel these out, remember that cosine is an even function, which means cosine of negative 2 pi over 3, I can just write as cosine of 2 pi over 3. That's because it's even, which means that this is, of course, using property 1, but now I'm going to rewrite it as cosine inverse of the cosine of positive 2 pi over 3. And we were only allowed to do that because cosine's even. So that's how I rewrite it. And now this cancels. I get 2 pi over 3. And is 2 pi over 3 in 0 to pi? Oops. Now, with that being said, reference the chart above the unit circle for cosine and look at that already. We see our answer. 2 pi over 3. It is there for us. So, we can say 2 pi over 3 is in the interval 0 to pi. Okay. Excellent. Next one. Cosine of the inverse cosine of pi. This is property 2, which only deals with numerical. So we have to see pi as a numerical value. And we know pi is a numerical value. 3.14, who cares, who cares, who cares, right? So these cancel, you're left with pi. And now we want to know if pi is in the interval -1 to 1. Is pi in -1 to 1? And remember, pi is 3.14 whatever, and 3.14 is definitely not in that interval. So we can say pi not in -1 to 1. And there's nothing we can do about it because this is numerical. Property 2 deals with numerical. Okay, there you go. Those are all the inverse properties for cosine. Now we get to tangent. Okay, here's tangent. And tangent is not 1 to 1 either. It constantly repeats itself. If I were to draw a horizontal line through it, again, we would intersect it infinitely amount of times. Intersect it infinitely. Yes. Okay. But again, is it possible to restrict a function's domain? That answer is yes. And the most common restriction for tangent happens to be from -pi/2 to pi/2. Not included. Because if you see -pi/2 and pi/2, these are vertical asymptotes. Okay, so down below shows you the restrictions. We have restricted tangent from -pi/2 to pi/2. So with that being said, I'll write the info down here. Here is our restricted tangent function. Its domain is now parentheses, work for me, -pi/2 to pi/2. Only because those are vertical asymptotes, so we can't include them. your range, negative infinity to infinity. There you go. Now, again, if I were to draw a horizontal line through this, I would only intersect tangent once, which means it is a one-to-one function, which guarantees it will have an inverse. Okay. So, next page, just like all the others, we'll work through this. Let's list all the important stuff about tangent. So I'm going to rewrite what I just wrote on the other page. Y equals tangent x, domain negative pi over 2 to pi over 2, range all reals, negative infinity to infinity. Okay, down below, we find the inverse, just like we've been doing. Step 1, done. Y equals tangent of x. Step 2, interchange. X equals tangent of y. 3, compose both sides with the inverse. You get inverse tangent of x equal to y. Step 4, state it as the inverse. F inverse of x equal to inverse tangent of x. Now, state the domain and range of the inverse. That means take the domain and range that you see at the top of the screen, flip them. So my domain is now negative infinity to infinity. My range is now negative pi over 2 to pi over 2. Okay, there we go. Graphically, you see the tangent functions. So the inverse tangent and the tangent. Again, these are symmetric about the line y equals x. You can flip points over if you needed to. And there you go. There's the inverse. Okay. Like I said, the most important part is knowing where our function lives. So tangent is very similar. The restrictions of the inverse tangent is very similar to the restrictions of the inverse sine. It exists from negative pi over 2 to pi over 2, which means we exist in quadrants 1 and 4 again. Except we cannot exist at pi over 2 and negative pi over 2. So this is the unit circle for inverse tangent. Okay, and there's 0, and again, we exist at pi over 6, pi over 4, pi over 3, negative pi over 6, negative pi over 4, negative pi over 3. So this is where the inverse tangent lives. This is where it hangs out. That's where it lives. Okay. Same restrictions as inverse sine. That looks like 4. There you go. Okay. Now, again, exercises, me again yelling at you. The inverse tangent is not the same as 1 over tangent. Inverse does not equal reciprocal. I don't think I have to write that again. Don't do that. Okay. Again, your calculators may be different. If you use a Casio, you'll get arctangent and throw it away. Go buy a TI. There you go. You get inverse tangent. That's for TIs. Okay. Down here, same thing. That's how you rearrange. This is how you compose to solve for the value of theta. So we've done this multiple times. So let's walk through it again. We're going to go down to solve A. So here we go. Let theta equal the inverse tangent of 1. Then compose both sides with tangent. Then tangent theta equals 1. But what value of theta does tangent equal 1 on the restrictions? Nope. Negative pi over 2 to pi over 2. Not included. So that means we reference our unit circle for inverse tangent. And which one of these radian values give me positive 1 for tangent? And you are correct. That's going to be pi over 4. Okay. So that's what we want. So this means that our answer here is theta equals pi over 4. Okay. All right, same thing here. Do it again. Let theta equal the inverse tangent of the negative square root of 3. Then tangent theta equals the negative square root of 3. But we have to find the radian value on negative pi over 2 to pi over 2. Okay. So we have to look. First thing we notice that this value is negative. That means when we come here, we should be looking in quadrant 2, because tangent will be negative in quadrant 2. All right. So to get a negative square root of 3, well, we have to look at the coordinates of the unit circle. If I did tangent of pi over 6, tangent of pi over 6 would put 1/2 over the square root of 3 over 2, which would be 1/2 times 2 over the square root of 3. So I guess I should be writing that down for you. If I said, what's the tangent of negative pi over 6, this would put negative 1/2 over square root 3 over 2, which would give me negative 1/2 times 2 over the square root of 3, which eventually would become negative square root 3 over 3, which we're not looking for. If I did tangent of negative pi over 3, that would put negative square root 3 over 2 over 1/2, which would give me negative square root 3 over 2 times 2 over 1, which gives me negative square root 3. So our answer is going to be negative pi over 3. Just have to know your unit circle, kids. So coming back here, passed it up. Our answer here is theta is going to be negative pi over 3. Perfect. Get in there, get in there. All right, here are the properties for the inverse tangent. It's the same things that go for cosine and sine. So just know that when you compose, you take the function's domain, the inside function's domain. That's it. We're not going to touch much on these. We're going to move on to the next one. Okay. Pause for a second. Okay. back to this one. Find the inverse function of f of x equals 2 sine x minus 1. The domain given is negative pi over 2 to pi over 2. Find the range of f and the domain and range of the inverse function. Okay, so some things noted. Let's see, this is the domain of f of x. So let's write that down somewhere. So I'm going to just list stuff for the original function. Oops. Nope. Stop. F of x equals, come on, we're doing so good. 2 sine x minus 1. The domain given was, my goodness, was negative pi over 2 to pi over 2. And the range we can find out. Okay, for the range, well, the normal range of a sine function is negative 1 to 1. But now look at the transformations going on this sine function. The 2 is a vertical stretch, which means you will multiply all your y values by 2. So this gets multiplied by 2. This means we get negative 2 to 2. But then one more transformation is the negative 1. That is a vertical shift, which means you will subtract 1 from these y values, which means that I get a new range of negative 3 and 1. That's it. That's as simple as it can get. You stretch them by 2, so now you go from negative 2 to 2. Then you shift them down 1, which means you go from 1 to negative 3 now. That's as easy as I can put it. Okay, now, with that being said, let's find the inverse. Step 1, make it y equals 2 times the sine of x minus 1. Step 2, interchange. X equals 2 sine y minus 1. Step 3, solve for y. So this means I'm going to add the 1 over. We get x plus 1 equals 2 sine y. Then I'm going to divide by 2. And we get x plus 1 over 2 equals the sine of y. And then I'm going to multiply both sides by the inverse. Not multiply, compose. Don't do multiply. Say compose both sides with the inverse. So I have sine inverse of x plus 1 over 2 equal to sine inverse of the sine of y. Okay. This means that we are left with sine inverse of x plus 1 over 2 equal to y. There you go. We have the inverse, so let's state it as such. For f inverse of x equals the inverse sine of x plus 1 over 2. Now state the domain and the range. come up here, flip these around, flip those, and we're going to get domain is -3 to 1. Range is -π/2 to π/2. There you go. That's what we're looking for. That was ugly. That's what we're looking for. Boom, 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 boom. There we go. Okay. Moving along. This is nothing different than what we did in 6.2 as well. The same steps to finding the inverse. All the same steps. The only thing new is the composition part. That's it. But we know how to compose now. Okay. All right. Last page. Solve the equations. So solve the equations involving inverse trig functions. So our job is to solve for x. So first thing we want to do is get sine all by itself, inverse sine all by itself. So first thing I'm going to do, divide by 3. This means I get inverse sine of x equals π/3. Okay. The next thing I'm going to do is compose both sides with the sine function. We've done this many times today. So the next step, this becomes x equals the sine of π/3. And reference your unit circle, and the sine of π/3 should be √3/2. That's it. That's what we do for that one. Okay. Next one, same thing. Divide by 4. Divide by 4. Inverse sine of x equals π/4. Then compose both sides with the sine function, and you get x equals the sine of π/4. And look at your unit circle. What is the sine of π/4? √2/2. That's it. Not bad. 3. 3 cosine inverse 2x equal to 2 pi. Again, get cosine by itself. So first step here, divide by 3, divide by 3. Left with cosine inverse of 2x equal to 2 pi/3. Then compose both sides with cosine. You get 2x equals the cosine of 2 pi/3. All right. Reference your unit circle. And what is the cosine of 2 pi/3? That should be -1/2. Now, all you do is solve for x, and you will multiply. You can divide by 2 or make your life easier. Multiply both sides by 1/2. And this gives me x equals -1/4. Cool. All right, still going. Let me just check my work. If I were to plug -1/4 in there, that would give me -1/2. Cosine inverse of -1/2 is 2 pi over 3. Yeah, we're good. Okay. Okay. Last one. For all the glory. All right. 4 cosine inverse of x minus 2 pi equals 2 cosine inverse of x. So remember, these are equations and we have to treat them algebraically. Algebra is involved in everything, even complex math, such as trig. So we have to think algebraically. So we look at this equation and we look for like terms, combine like terms. Well, you see the like terms, 4 cosine inverse of x, 2 cosine inverse of x. They have the same term and same variables. And in this case, our variable is the trig function, the inverse cosine of x. So we're going to want to combine those two functions. So what I'm going to say is minus 2 cosine inverse of x minus 2 cosine inverse of x gives me 2 cosine inverse of x minus 2 pi equal to 0. See? Completely algebraic as it is. Now, we want cosine by itself, so we'll add 2 pi over to the right. 2 cosine inverse of x equal to 2 pi. Then divide by 2, divide by 2. You get cosine inverse of x equal to pi. Then, once we get to this step, apply, well, not apply, compose both sides with cosine, and we'll end up with x equals cosine of pi. Now look at your unit circle, and what's the cosine of pi? -1. There you go. That is it. That is 8.1. We learned inverse sine, cosine, and tangent. Yes, I will send you these notes, and I will also send you the YouTube video. But that is it, kids. Awesome.